Hello, it's lec134, lecture 39. Last time we were doing the bivariate normal, and new properties that we learned was the equation of the regression line, which of course when x and y are in standard units is y is rho x, but if it's not in standard units we have a slope rho sdy over sdx and a y-intercept given in below. So we say that xy is bivariate BV. Notice that it has 5 parameters to determine that line. So the regression effect was another thing we learned, which makes the predicted scores regress towards the mean. That is the mean of y. So we're going to be using moment generating functions today. So let's just recall what a moment generating function is: the expectation of e to the ty, which you can also write as the moment generating function of ty of 1. And there's a multivariate moment generating function that's defined by expectation of e to the sx plus ty, which you can again also write as the moment generating function of the random variable sx plus ty of 1. So, and also recall that z is z is normal mu sigma squared if and only if z's moment generating function is given in the formula there. So today we're going to look at the student responses of the concept test from last time and look at properties of the bivariate normal and practice with the bivariate normal. Next time we're going to start to review. I'll post a discussion board on B courses so you can list your topics that you want to go over. So last time we saw this concept test, and you guys said some interesting things, some interesting correct things. The regression effect makes the score closer to the mean. That's right. And another good comment: the predicted score for the physics test using the regression line will yield a predicted score less than 75 for a math score of 75. Therefore, a student would have to have a score above 75 on the math test to get a 75 on the physics test. And fewer students did this because the test scores are distributed normally. I've never heard that explanation before, but it sounds great. So there's several properties of bivariate normals you guys need to know. So one is that actually, what is the moment generating function for a standard bivariate? So we're going to show that the moment generating function is e to the s squared over 2 plus t squared over 2 plus st rho. And to do this, we just use the definition, and then we use, so then we write expectation of e to the, there's a coefficient for x, and e, some constant for z, and using the fact that x and z are independent, we can write the expectation of a product as the product of the expectations, and this is these are moment generating functions for x and z for different constants, and we can write down what that moment generating function is, and lo and behold, we get out the moment generating function that we're supposed to. So that's a very nice result. We know the moment generating function for the bivariate normal, and x and y is bivariate normal, then xy has correlation 0 if and only if x and y are independent. So we know that independence implies correlation is 0, but actually it goes the other way as well. And so we can prove this using moment generating functions. So we write out so the bivariate moment generating, the multivariate moment generating function, m of xy st is, we can write this as the moment generating function of sx plus ty, and this and here, this we know that the moment generating function for two independent random variables can be written as a product of the independent moment generating function. So we get is equal to msx1 times mty1, which then is the same as mxs myt. So the point is that the moment generating function, a bivariate moment, the multivariate moment generating function splits as a product exactly when x and y are independent, and we know the moment generating function for the bivariate normal, and so we can see that does indeed split exactly when rho is 0. So rho is 0 is equivalent to x and y being independent. So furthermore, x and y, if x and y are standard normal and have correlation rho, then being standard bivariate normal is equivalent to sx plus ty being normal for all constants s and t. So this has a straightforward proof. If xy is standard bivariate normal, then we can just substitute what y is into sx plus ty to see that we get an expression that's a linear combination of x and z, and we know that linear combinations of independent random variables is normal. And the converse is very easy because we know the moment generating function for the bivariate normal. So we have that if sx plus ty is normal, then sx plus ty is normal 0, s squared plus t squared plus 2st rho, and we can write the moment generating function for mxy, and we see that this is precisely the bivariate normal moment generating function if sx plus ty is normal. So it's right there. This has an important corollary, and that is, in the above theorem, we did it when x and y were standard normal, but actually, if x and y are just normal, then xy being bivariate with those 5 parameters is equivalent to sx plus ty being normal for all constants s and t. And I'll let you read this explanation here, but essentially it just comes down to what's the definition of x and y being bivariate normal. That is, x and y is bivariate normal if when you put x and y into standard units, it's bivariate, standard bivariate normal. And furthermore, sx star plus ty star is normal if and only if sx plus ty is normal. So it just follows from this. So then I had you do this problem here where you needed to find the chance that a student scores higher on the final than the midterm, and you used the fact that because FM is bivariate normal, because MF is bivariate normal, F minus M is normal, and so we could then figure out this probability in terms of the CDF. We then did a concept test, and we we had that it's true that if xy is bivariate normal, then 2x plus 3y plus 4 and 6x minus y minus 4 is bivariate normal, and that follows just because xy is bivariate normal, we know that any linear combination of x and y is normal, and so any linear combination of 2x plus 3y plus 4 and 6x plus minus y minus 4, which you can write as a linear combination of x and y, so that follows that that's going to be normal, and adding a constant to a normal is normal. So we've shown that any linear combination of 2x plus 3y plus 4 and 6x minus y minus 4 is indeed normal, and hence bivariate normal. So I have some extra goodies here for you, but I don't have time to go over it, namely a proof of the CLT, which we can show using moment generating functions. I'll let the interested people read this, but it's a beautiful proof in my opinion. And also just an extra, oh yes, and I also have an example in case you're wondering if x and y are standard normals, is it true that the joint of x and y is necessarily standard bivariate? And in fact, it's not. So I've provided an example where it's not. You can read that, and just an extra problem to calculate. But that's the show, guys. I'll see you for review on Wednesday. Bye-bye.